Cryptography, or the technique for secure communications in the presence of an adversary, is one of the most interesting topics in cybersecurity. It helps secure trillions of dollars moving through global banks, has helped win world wars, and today is one of the main reasons there's any sense of digital privacy. Every time you visit a web page or unlock your phone, some form of cryptography is working under the hood to secure your data. Unfortunately for how interesting and important it is, it's incredibly hard to understand. Modern cryptography is based on a ton of mathematical theory, and without a PhD and a special type of autism, it becomes really hard to digest. I mean, this is the explanation of just one encryption algorithm. This, and this, and this, and this, and this, and this. Now, all that is just proving that the algorithm is secure. Because of mathematical limitations that I'm not going to pretend to understand, there's no such thing as a perfect encryption algorithm. Every algorithm is theoretically breakable, but the creators of these algorithms designed them around what's called the computational hardness assumption. This just means that while given unlimited resources, you could break the algorithm, the amount of time or compute it would take to do so is so infeasible the algorithm is considered computationally secure. So using practical assumptions about time and compute power, the algorithm is unbreakable. Of course, these assumptions, at least about computing power, are dynamic. Computing breakthroughs like quantum computing would completely change the threshold for computationally secure. Now, we're getting off in the weeds here, which is incredibly easy to do when talking about cryptography. So, to define the topics and scope for the rest of this video, we are going to explore the three main categories of cryptography from a high level. We're going to avoid the granular details and the underlying math and focus on the basic flow and some examples of when you might use each type. To begin, let's define the three main categories: symmetric key encryption, asymmetric key encryption, and hashing. Now, so far in this video, you've heard the words cryptography and encryption used seemingly interchangeably. However, these words refer to slightly different things. Encryption refers to taking some data and scrambling it up so no one else can read it, and then being able to unscramble it. Encryption is a type of cryptography. The other type of cryptography is what's called hashing. Now, hashing lets you take what is essentially a digital fingerprint of some data. Now, that probably doesn't make any sense, so let's take a closer look at hashing. Hashing lets you take any piece of data and produce an output that's unique to that piece of data. The same way you could take a person's fingerprint and have a unique identifier for that person, hashing lets you have a unique identifier for any piece of data. Now, you may be asking yourself, is it really any piece of data? And to clarify, while some hashing algorithms truly have no upper limit, others do. For example, the most popular hashing algorithm, SHA-256, has an upper limit size of 2 to the power of 64 minus 1 bits, which comes out to approximately 2.3 exabytes. But as far as I'm concerned, that's a fake compute unit. So to put it into practical units, that's over 19 million copies of GTA 5. So even if you choose a hashing algorithm with an upper limit, it's so astronomically large that in practice you would never hit it. I can almost guarantee that you would hit a memory constraint before you would hit the upper limit of the hashing algorithm. So for all practical intents and purposes, hashing algorithms take an arbitrary sized input. This could be anything from a single word all the way up to 19 million copies of GTA 5. When you run the input through the hashing algorithm, you will get some output. This output is often referred to as a hash or a digest. So when you hear hash or digest, just think of the output of a hashing algorithm. Now, the key feature of the digest is that it's fixed sized. This means that no matter the size of the input, you will always get the same sized output. For example, both the single word and all the millions of GTA 5s will both result in the same size digest. The example you see now has a digest size of 256 bits or 32 bytes. The exact size of the digest will be determined by the specific hashing algorithm that's used. But the same algorithm will always produce the same size digest, no matter the size of the input. These algorithms are also deterministic, which means that the same input will always result in the same digest. No matter how many times we input hello into this hashing algorithm, we will always get the same digest. But even one small change to the input, like capitalization or punctuation, will result in a huge change in the digest. The final defining characteristic of a hashing algorithm is that they are one way. It's easy to take an input and compute its associated digest, but just given the digest, it's extremely hard to compute its associated input. This fits in well with the fingerprint analogy. Given a person, it's really easy to take their fingerprint. But just given a fingerprint, it would be extremely hard to match that print to a person. You would have to go around and compare the fingerprints of everyone else until you found a match. The same is true of hashing. Just given a digest, there's no intelligent way to reverse engineer the input. Your best bet is to guess and check. And while it is theoretically possible to guess and check your way to a match, it's so computationally infeasible. So we know that hashing algorithms take an arbitrary sized input, produce a fixed sized output, are deterministic, and are one way. This sounds pretty cool, but when would you actually use this? Well, this is exactly how websites store your passwords. Rather than storing them in readable text, which would mean a hacker who steals the database instantly knows everyone's logins, they just store a hash of your password. When you log in, the site takes the password you entered, hashes it in memory, and compares it to the stored hash. If they match, you're in. The key point is that your real password is never written to long-term storage. And because hashes are one way, an attacker who steals the database is left with nothing but gibberish. Their only option is to guess and check. Now this seems fine and dandy, but there is still one problem. We have an infinite amount of potential inputs, literally any combination of zeros and ones, but a finite amount of potential outputs. There's only 2 to the power of 256 unique hashes. Even if you choose a hashing algorithm with an upper limit size like SHA-256, you would still have 2 to the power of 2 to the power of 64 minus 1 potential inputs, but only 2 to the power of 256 potential outputs. This means that there must exist 2 unique inputs that result in the same digest. And this seems to break the entire theory of hashing. I mean, look at our user database example. This means that it's possible to have 2 different passwords that result in the same hash. So theoretically, somebody could log into your account using a completely different password. But hashing is still widely used and considered secure by modern standards. So how are these two things reconciled? Well, to answer that, we need to take a closer look at the number of unique hashes. The examples we've dealt with today have 256 bits, meaning there's a total of 2 to the power of 256 possible unique digests. Now, when you write it like this, it doesn't seem that grand, but what if we write it like this? Pretty crazy looking, right? For reference, this is a trillion, and this is the estimated number of stars in the observable universe. To guarantee finding a collision, or 2 inputs that result in the same digest, you would need to try 2 to the power of 256 plus 1 inputs. Even using the birthday paradox to find the average amount of inputs to find a collision, you would still need to try 2 to the power of 128 random inputs. It's just so astronomically unlikely. So unlikely that it's hard to even comprehend. For example, if you had a computer that could compute a trillion hashes a second, and you had this computer running since the Big Bang, you would still fall unimaginably short of statistically finding a collision. So it should come as no surprise that researchers have yet to find a SHA-256 collision. Some hashing algorithms even use a 512-bit digest, and for shits and giggles, this is what that would look like. So theoretically, while there could be a collision or a brute force attempt to reverse a hash, it's so incredibly unlikely that hashing is considered computationally secure. Okay, that was a lot, but I promise that's as technical as it'll get. Before we jump into the 2 kinds of encryption, I want to define a few terms. The first is key. Now we'll be looking at 2 different kinds of keys today, but we'll differentiate those later. For now, a key just refers to a piece of information, usually a random string of bits, that's taken as an input into an encryption or decryption algorithm. The key is what makes the algorithm usable and reversible. Without the right key, you can't unlock the right output. Next is plain text. This just refers to any human or machine readable data. For example, all the text you see on the screen right now is plain text. Finally is ciphertext. This refers to the scrambled or encrypted output that's produced after plain text is encrypted. Okay, with these out of the way, let's start with symmetric key encryption. So what differentiates symmetric key encryption from asymmetric key encryption is the type of key used. As the name suggests, symmetric key encryption uses a symmetric key, meaning that both encryption and decryption is done using that same key. So for 2 people to use a symmetric key algorithm, they would both need access to the same key. So the encryption algorithm will take plain text along with the shared key and produce a ciphertext. The decryption algorithm will take that same key along with the ciphertext and produce the original plain text. So let's say, for example, Alice wants to send Bob the message hello, and both of them have already agreed upon the shared key 123. Now in reality, keys are much longer and much more random, but for the sake of example, we're going to use 123. Alice would take the plain text hello along with the shared key 123 and run them through the encryption algorithm. This would provide a ciphertext. Now the ciphertext can be freely shared. You can hand deliver the ciphertext to an adversary, and operating under the assumption that Alice and Bob are the only ones with the shared key, your message would be safe. Once the ciphertext is shared with Bob, he would take the shared key and the ciphertext, run them through the decryption algorithm, and would be left with a plaintext message hello. Okay, that's symmetric encryption. There's still one big question though. How do both parties get the same secret key in the first place? I mean, Alice can generate the key, but how does she securely get it to Bob? That's an excellent question, and the answer to it is asymmetric key encryption. Asymmetric encryption employs a two-key approach, a public key that's known to everybody and a private key that's only known to the owner. Rather than having just one key that everyone uses, each individual has their own pair of public and private keys. As the name would suggest, these keys work asymmetrically, so what's encrypted with one can only be decrypted with the other. So encrypted with the public key is decrypted with the private key, and encrypted with the private key is decrypted with the public key. This approach lets you do some pretty cool things. Let's say, for example, Alice wants to send Bob a message, but she wants Bob to be sure that the message came from her and couldn't have come from anyone else. Using Alice's key pair, she could encrypt the plaintext with her private key. She would then send this ciphertext to Bob. Bob could use Alice's public key, which is available to anybody, to decrypt this plaintext. If the text is decryptable with Alice's public key, you know it was encrypted with her private key, which we assume only she has access to. This gives Bob the assurance that the message he received could have only come from Alice. This proves authenticity, meaning that the message came from who it's claimed to have come from. No one else but Alice could have sent this message. But it does not provide confidentiality. Since Alice's public key is available to everybody, anybody, not just Bob, could decrypt this message. Let's look at another situation where Bob wants to send a message to Alice but wants to be sure that only Alice can read it. In this case, we're looking for confidentiality, not authenticity. Bob could encrypt the plaintext with Alice's public key. Now the ciphertext can only be decrypted with Alice's private key, which we assume only Alice has access to. This means that Alice is the only one who could decrypt this message. Okay, with the foundation of symmetric and asymmetric encryption down, let's take a look at an example of how these two could be used in tandem to answer our previous question about how both parties securely get the symmetric shared key. Before we begin though, you may be wondering why even bother exchanging the symmetric key. I mean, if we both already have asymmetric keys generated that allow for secure communication, why not just use asymmetric encryption? Well, the answer is you could. However, symmetric encryption is generally faster, so for use cases like secure web browsing, where a lot of data needs to be encrypted and decrypted in real time, it makes sense to take the extra time to exchange a symmetric key. Okay, let's take a look at an example of what this might look like. Alice will generate the symmetric key. The symmetric key will be the plaintext for our asymmetric exchange. With that key as plaintext, and using Bob's public key, Alice can create a ciphertext. That ciphertext can be shared to Bob and decrypted with his private key. Again, assuming Bob is the only one with access to his private key, no one else should be able to decrypt this ciphertext and figure out what the symmetric key is. With that key exchange, we can proceed with traditional symmetric encryption. Alice can create a message she wants to send Bob. She could then encrypt this message with the shared symmetric key and send the generated ciphertext to Bob. Bob can use the same key and the ciphertext to decrypt the message and receive the plaintext that Alice originally sent. And that's the big picture of cryptography. We've looked at hashing, symmetric encryption, and asymmetric encryption. While individual algorithms may differ in their specific implementation, this general flow of how each type of cryptography works is universally true. I want to thank you for your time today and hope you found this interesting and informative. As always, all the code used in this video, along with links to the articles referenced, will be available on GitHub. Until next time, thank you for watching.